So, I propose that we start. It's okay for you? Yeah, and it's about the master thesis defense of Albert Einstein Nota. The jury is composed by the three supervisors, so myself, Bruno, and Nicolas, and by François Just, officiellement, oui, as he's also responsible for the master in general. So then we have the grand public. Okay. So the idea is François wrote between 30 minutes and 45, but I think we would like to stick on 30 minutes, if possible. If I hope it's okay for you, and then we have questions by actually everybody here, but we will start with the jury members and then also free questions. Okay, good. So let's go.
How do we dim the lights?
Sorry? You can put on conference, on seminar. It's okay?
Okay, so hello and welcome to my thesis defense. I'm not Albert Einstein, and I'm going to present you the work that was done during my master's thesis, which consisted of developing an automatic pointing model for Euler. The work was conducted under the supervision of Francesco, Bruno, and Nicola. Okay. So here's the outline. I'll start by outlining the project objectives, then we'll have an introduction in the background, then we'll go through the methods that were used in this study. Then I'll present the results. We're going to conclude and close with some acknowledgements. So in a nutshell, the goal of the project was to modernize Euler Telescope's pointing capabilities via an automated, accurate, and maintainable pointing model. In particular, an understanding of the principles and mechanics of the telescope, of telescope pointing models and their role in control systems. The participation in a technical mission at La Silla during the academic year, during which hands-on data collection would be done relevant to the studies. The usage and adaptation of the modeling software that we use in this process, that software is known as C-Point, and integration of the final pointing model into the new telescope control software, ensuring that it works, that's compatible, and that it's also stable. And then ensuring that the full pipeline from data acquisition to deployment is operational, that it's robust and also reproducible. And lastly, clearly document all aspects of the routine for future maintenance and development. So for the scientific and technical context, in ground-based astronomy, telescope pointing performance, which is defined as the ability to direct and maintain alignment with celestial objects, is critical. For example, if you take a look at the image on my left, we'd notice that there are trails that are left by the stars in this image. And these trails depict movement. But it's not the stars themselves that are moving. They don't move this fast in the sky. Rather, it's the rotation of the Earth, which causes an upward motion of these stars in the field. This means that we need to constantly adjust our telescope so as to accurately track objects in the sky. Else, we are going to have systematic errors, and this will definitely affect the data quality and hence observational efficiency. So if you wanted to, let's say, carry out photometric studies, high precision photometric studies with this image, it wouldn't be possible because the image is not of good quality, and this is clearly a limitation. We want to avoid that. So the point is we want to be able to accurately point at a target, but also track it adequately so as to avoid these errors. Now, the first question we want to ask ourselves here is, how do we locate objects in the sky? And here comes the coordinate systems. Two of them in particular. We have the horizontal coordinate system. So in this system, picture the observer like a point somewhere on the spherical shape of the Earth. And then we imagine a tangent, a plane that's tangent to the Earth at the observer's location. The intersection of this plane with the sky is known as the observer's local horizon. The north, of course, is directed towards the Earth's north pole, and then we have the other three cardinal points. From here, if you want to locate an object in space, then we are going to use two great circles. The first will define the altitude. The second will define the horizon. So we use alt as coordinates in the horizontal coordinate system. Then the second is the equatorial coordinate system, which has this particularity that it's fixed with respect to the stars. We have in particular the celestial sphere, which is kind of an imaginary sphere that is aligned with the Earth's polar axis. The celestial equator here is a projection of the equator into, on this sphere. And if you want to locate an object in this system, then just as we locate objects on Earth using latitudes and longitudes, in this case, we are going to use right ascension, which is kind of the longitude on this sphere, and declination, which is some sort of latitude. So the right ascension being measured from a reference point known as the vernal equinox, and the declination measured from the celestial equator, so that plane. Now, the next question is, which telescope mount do we use? And the mount type that we are going to choose will determine the coordinate system that would be used. There are two of them, two main ones. The first is the alt azimuth mount, which are going to employ the alt azimuth coordinates. So here we just have a flat base that constitutes the mount, and our telescope is mounted on this base in such a way that if we want to locate any object in space, we can use the altitude and the azimuth, just as we saw on the previous slide. The second mount here is the equatorial mount. So in this case, we want our mount to be, the axis of our mount to be aligned with the celestial pole in such a way that if we want to track an object, we can use the declination and the right ascension. Now, the next question is, how do we transform between these coordinate systems? Usually in catalogs, we have the coordinates of object being given in the equatorial coordinate system because it's fixed. It doesn't change with time. But then we need to take into account some subtle corrections. For example, proper motion, the fact that the stars have individual motions with respect to the solar system. Precession and nutation, which is the fact that the Earth is kind of a sphere and it's subjected to external torque, so it wobbles. We need to take this into account. We have aberrations, which are due to the movement of the Earth. The Earth rotates, but also it orbits the sun. We have also the fact that the Earth has an atmosphere, so when observing objects, light is going to be refracted as it passes through these atmospheric layers. So after these corrections are accounted for, we then need to convert the coordinates RADEC into the relevant system that corresponds to the mount of our telescope. In the case of an all-earth mount, we make use of these transformations. So that takes into account the altitude, the observer's location, and the time. And in the case of a horizontal mount, which is aligned with the celestial sphere, we just need, for tracking, to ensure that we take into account the observer's local time, because the right ascension coordinate is fixed, but the Earth is rotating with respect to that point. So we need to take into account that movement. Where comes the local sidereal time? So we're essentially going to be using the hour angle and the declination in this system. In practice, these transformations are not done manually. They're handled in telescope systems and modern software tools. So now, what's a pointing model? Let's suppose that we want to point our telescope at a target A. This is what I call here the real target. In practice, the telescope would always miss that target. It's going to point somewhere around at B, which is the pointing target, and there is an error. This arises because actually the engineering fails us, and there are a set of errors that are going to add up, and the result is this pointing error. So the idea is to be able to design a mathematical framework that models these errors in such a way that we can take our telescope from point B back to point A, where it's supposed to be. And that's a pointing model. In practice, the way we do this is that we are going to measure the deviations across a grid on the sky and then model this using standard software tools like T-Point or other softwares. So in order to depict how these errors arise, where they come from, I here illustrated the axis of an azimuth mounted telescope. There are three of them. We have the azimuth axis, the altitude axis, which contains which controls the altitude, and the pointing axis. So this is in an ideal case when everything is perfect. These three axes form a Euclidean coordinate system. They are perpendicular pair by pair. And then let's take a look at what happens if we just introduce a slight non-perpendicularity between a pair of these axes. So you'd notice that the yellow axis is where we are pointing, and the red is where we were supposed to point if things were ideal. So just introducing a slight non-perpendicularity between a pair of axes introduces a pointing error. And these are the type of errors that we want to be able to model and thus correct for them. So here we have all a list of the possible sources of errors for an azimuth mounted telescope. These terms can be divided into two categories. We have the geometric terms, which are errors that arise due to the geometry of the mount. We have the first ones, IA and IE, which represent index errors in azimuth and elevation. So actually, these are deviations from the zero position of the telescope. We have the non-perpendicularity of the axis, of the azimuth and elevation axis. So if things are under an ideal situation, they should be perpendicular, but in practice, they might not be. We have the collimation error, which measures the non-perpendicularity between the pointing axis and the altitude axis. And then we have AN and AW, which model errors that arise due to a tilt of the azimuth axis, so that vertical axis, north, south, or east-west. On the other side, we have the non-geometric terms, which are those errors that arise due to environmental factors or some other factors that are not necessarily linked to the geometry of the mount. The first one here is the tube flexure. So the telescope is actually a tube, okay? And according to Hooke's law, if you have a body that's subjected to stresses, the telescope's weight, then it's going to deform, it's going to bend. So we need to account for this tube flexure, which is a source of error. Also, we have thermal deformations, the fact that if there are temperature fluctuations in the environment of the telescope, then the tube deforms, and we need to take this into account. And lastly, we have nonlinear effects, okay, that are also modeled with polynomial and harmonic corrections to ensure that any remaining systematic error can be modeled. In particular, that's not linear. So all these errors represent systematic, reproducible, and errors that can be modeled mathematically. So we model them in order to be able to apply the required corrections. Now, a few words on the Euler Telescope, which is the telescope which I worked on for this thesis. It's a 1.2 meter telescope located at La Silla in Chile. It employs a Richer-Chrétien optical design, which consists of two spherical mirrors, so the primary and the secondary. And this is useful to eliminate some high-order aberrations like chroma aberration, like spherical aberration. It employs an alt-azimuth mount. So in this case, we are going to be working with the relevant equations and transformations relative to this mount, so the alt-azimuth system. And it has three instruments. We have ECAM, which is an imaging camera, and it has the widest field of view among the three instruments. It's located at the telescope's Cassegrain focus. So here, just at the tip, we have CORALIE, which is a high resolution, is a shell spectrograph, which has a narrower field of view compared to ECAM. And it uses we make use here of a guiding camera that helps us to center the star. Since it's a spectrograph, we need to analyze the light coming from maybe stars. So we make use here of this guiding camera that helps us center the star inside a hole. Light enters that hole and then is directed to the spectrograph for analysis. And lastly, we have CALAO, which is an adaptive optics imager. It has a much narrower field of view and the highest resolution of the three. But I mean, as of this presentation, it's not fully commissioned. And it's located at the NASMIS focus. So CORALIE and CALAO are each located on the NASMIS focus on the side here, and then the other way. So now I'll take you through the methodology, the steps that were employed in order to develop a pointing model for our instruments. The first step is usually the data acquisition. We need to point our telescope at a regular grid on the sky, then measure the offsets, fit a model, and once the model is validated, it's going to be deployed. So starting with the data acquisition, as Ella said, the idea is to point our telescope on a grid in the whole hemisphere to ensure that we have a good sampling. And in particular, what we want to do here is to be able to measure the raw pointing of the telescope. So typically, what we may want to do here is to reset any pointing model that might be running to 0. So ensure that if we command the telescope to point at a certain target, any error that will be introduced will just reflect the raw behavior of the telescope. And that's what we do for ECAM. And what we want here is just to be able to have enough stars in our field so as to be able to measure the offsets using a technique I will describe in the next slide. Now, for CORALIE, this method poses some issues. In particular, if we reset the model to zero. It's important already to make the distinction that for CORALIE, we have like an old paradigm and a new paradigm. So the new is what emerged from this thesis. So in the old paradigm, resetting the model to zero poses a problem, which is that we are going to miss the star, and the star might not be in the field of view, which is problematic because this method relies on the presence of that target, of that star, for example, in the field. So what we want to do here is to apply a certain trick. So rather than resetting the model to zero, we are going to use an existing pointing model for ECAM, for example. And this at least would ensure that when we command our telescope to point at a certain target, we are going to have that star at least in the field. And this would enable us to measure the offsets. I'm going to describe that on the next slide. But then in the new paradigm, we want to avoid a lot of issues related to the transformation. This is something we commonly face with this older method. And this actually consists of resetting the model to zero, for CORALIE, just as with ECAM, but ensuring that we have a sufficiently long exposure with the guiding cam so that we have enough stars in our field. And doing this, we can actually employ the same method as with ECAM. So going to the measurement of the pointing offsets, what we want to do here is, as Ayala said, to compare the actual pointing of the telescope with the commanded coordinates that were entered. Now, for ECAM, the model was reset to zero. We have an image. There are stars in that image. And what we want to do is to determine our pointing direction using the stars in that image. And a technique that is employed here is astrometric platesolving. So this consists of, it's an algorithm that's going to analyze the image, identify star patterns, and then compare it, try to match the pattern to those of images in its catalog. And once it finds a successful match, it can generate us a transformation that would enable us to convert any pixel position on our detector to the corresponding sky position. So it's very effective, and it enables us to easily deduce our actual pointing direction, just having stars in our field of view. Enough stars, for that matter. So typically, like 6, 7 stars are enough to have a successful pattern match. So here are some softwares that enable us to do that. We have astrometry.net, we have SCAMP, and there are some other softwares. Now, with CORALIE, in the old paradigm, we made use of an existing pointing model. So here we have a depiction of how this works. So here in the middle is the position of the hole, of the fiber hole on the image. So if things were perfect, this target would be inside that hole, but it's not. But at least it's somewhere in the field of view. So what we want to do here is to measure this offset, this distance, and transform it into sky offsets. This employs a transformation matrix M that I depicted here. And in the course of the project, one of the things I did was also a recalibration of that matrix, because there were rough pointing errors for CORALIE. And this was traced actually to this, the cost was traced to this matrix. So I recomputed it. And actually what I got was a reflection matrix, this one. And the one that was there before was a rotation, a 90 degrees anti-clockwise rotation. So these two, they look similar. We might notice that actually the difference is just this minus sign. but the geometrical effect is totally different. So this really came to solve this pointing issue. So we have that matrix well calibrated, and we can map any pixel offsets into sky offsets. And then the last thing we want to do here is to remove the corrections that the ECAM pointing model we introduced applied. So it was kind of, we had a bias at the beginning, but at the end we need to remove it so that we can get back to the actual, to the raw pointing of the telescope. So this legacy method clearly is indirect and it's not straightforward. And they were, we are prone to a lot of issues, to a lot of errors. Reason why in the new method, we are going to essentially just do exactly what we do with ECAM for CORALIE. So we point our telescope on targets at a regular grid in the sky. We have an image where there are enough stars. We plate solve it to determine our pointing direction, and that's it. So it's simpler and more effective. The result of this process is then the pointing data, which is a table consisting of the commanded coordinates and then the raw coordinates of the telescope. So like where we ask the telescope to point and where it actually pointed. And this depicts indeed our offsets. Having this data now, we can move to the next part, which is model fitting. And for this, we need three things. We need data, we have the data. We need a fitting framework, and we need a model to fit to the data. So starting with the fitting framework, there are two frameworks that were employed in this work. We have T-point, which is the standard framework used by many observatories in the world. It was developed by Patrick Wallace, I think of Caltech. And typically it works as a black box. You load your data in the input, it performs something here in the middle, and at the output, you have your best fit parameters. So inside this black box, actually, I took a look, but I darkened it just to depict the fact that, it really works like a black box. Since we have a license of this software, I could have a look at what it does. So in this black box, essentially what is done is SVD-based least squares fitting. So it's kind of a robust algorithm that uses the least squares estimator and is particularly useful at constraining the parameters. On the other side, we have a custom Python framework that I developed. So actually developing this was initially not in the objectives of the project, but it came to be an important and useful addition for me as a student, but also a nice contribution to the project, because since it's fully scripted in Python, we can easily customize it for our pipelines for the various instruments. And that's what was actually done. The method I use here is essentially just ordinary least squares optimization using a numerical algorithm known as TRF. And as I shall present in the result, this was tested and validated against T-point. So in the new telescope system, this is going to replace T-point. Having now our fitting framework, the next thing we want is a model. Now, the way we establish a pointing model is, since we identify the mounting of our telescope, and we know that usually this mount is not perfect, so there are going to be errors that are introduced. So we'll start with the geometric terms. So IA, CA, AN, AW, yeah, those terms. We fit these terms to the data, and we analyze the residuals. Looking at the residuals, we are going to detect any patterns, any structure, and that way we are going to add additional terms so as to reduce as much as possible the residuals. So here is the model that we have that we are using on Euler for the various instruments. It's a model that has been used for many years now. So we have our framework, we have a model, we have fitted a model, we have the values of these terms, these pointing terms, and we have the statistics of the fit. The next thing we need to do is to validate the model. So typically, to assess the accuracy and reliability of the model, we don't employ just one method. There's a set of criteria that we want to assess. The first is the RMS of the residuals. So we look at the RMS. If it's low, typically below like 5 arc seconds, then it's an indicator of a good fitting process. So lower RMS implies better model fit, but care needs to be taken care of here of overfitting, because you can sometimes have a low RMS, but there is overfitting, which means that the model might not perform well in other regions of the sky. Reason why we have several validation criteria. The next thing we'll look at is the distribution of the residuals in azimuth and elevation. So we want to check if there is some symmetry, if there are no systematics, which would indicate a good fit, and thus that the pointing model is also good. Then one thing we can also do is to assess the pointing of the telescope under long exposures. Because you remember from the introduction, we don't just want to point, but we also want to appropriately track the target in the field. So we are going to analyze the geometry of stars in the image. And a good pointing model that's tracking correctly should keep the stars almost perfectly round. So that's what we look at here. If not, it means, okay, we need to evaluate, to reevaluate, to possibly reevaluate the pointing model. And lastly, what we may just want to do is to load the terms in the telescope control system, point the telescope at random targets in the sky, and then just measure the pointing error. If it's low, then it's indicative of a good performance, typically. Yeah. So once we are up with the model, once it's validated, we are going to load it into the telescope software, and the corrections are going to be applied in real time. So now let's look at the results. So here is a 2D map of the corrections applied by our pointing model on the sky. What we can notice is that the highest corrections, if we look at the total corrections, are towards the horizon, which is due to the fact that when we point at low altitudes, there is atmospheric refraction that increases as we go to lower altitudes, but also there's a tube flexure that dominates. So this accounts for an increased correction towards the horizon compared to the zenith. Now, a quick look at the pointing models that we obtained. So here for ECAM, we acquired 24 data points. On a spiral grid, you can see the spiral structure here. Before fit, this is what we have. if things were perfect, then all these points should have been at the center of that circle. So the approximately 300 arc seconds that we see here represents the pointing error. And after fitting, you can notice that we succeed to appropriately model these errors and bring all the points, most of the points, to less than 2.5 arc seconds, which is a very good performance. Then for the old method, which consisted of measuring the offset and then mapping them to the sky, for CORALIE, we have, again, the pointing error around 290 arc seconds. Then after fitting, most of those points within 2.7 arc seconds. So that's also very good. With the new method for CORALIE, so using astrometric plate solving, again, before fit, around 300 arc seconds. So that depicts the pointing error. And we can notice something here. After fitting, most of the points are within 1.5 arc seconds, which means that the modeling here is even better and more accurate than what we had with the old method. So you can compare this and this. All of these sky RMS are acceptable, but we can clearly see that using the astrometric method, we have an improved accuracy compared to the legacy method. But right now on Euler, these are the terms that are running for ECAM, and then for CORALIE, this one. But henceforth, this is the method we are going to be employing for CORALIE. Okay, so now a comparison. Here we have a comparison of my custom Python fitting framework with respect to T-point. So using the ECAM data set, I first of all fitted the model to the data using my framework. So here are the results. We have histograms of the residuals. We have the residuals as a function of azimuth and elevation. But what interests us here, the most important, is this top middle plot. We can notice that the residuals in azimuth and elevation are mostly within 1.8 arc seconds. So it depicts the fact that the model does a good job. And here we have the fitted terms. So the total RMS, 1.8 arc seconds, that's good. The population standard deviation. And we can notice that there are quite many terms that are correlated. But actually, the correlations of these pairs is not really linked to a physical effect. It's more of a mathematical artifact, because the method that I employ here, the algorithm, is not very robust at constraining the terms for ill-conditioned problems. Essentially, there are problems where if you just have a slight change in the input, you have to make a very big change in the output. So yeah, that is actually a limitation of this approach, but the results are good and usable. Now, here's a comparison between on the ECAM data set between my model and my custom Python framework and T-point, and you can notice that there is very good argument across most of the sky to better than 2.5 arc seconds. There are, of course, minor differences, which is due to the fact that the fitting algorithms used are not the same. So this is normal. You should expect this. So in an attempt to simplify the pointing model while maintaining performance and improving numerical stability, so to avoid risk of overfitting, I proposed a new pointing model, actually a new framework, which essentially replaces these bottoms with this trail. Essentially, TF, the standard two flexure, which assumes Hooke's law, so that the deformation is directly proportional to the stress, is replaced with TX, which actually accounts for the fact that usually when you go to low elevations, the deformation tends to become nonlinear. So this seems to better model the flexure. And then we have these harmonic terms that account for a good fit overall. So now just a quick look at a comparison between the alternative model and the current one. So here again, I just fitted to the same ECAM data set, the new model. we see that the RMS, most of the points are contained within 2.3 arc seconds, which is actually a very good performance. And then if we compare the new set of terms with the current one, we notice that there is also a very good agreement to mostly within 0.7 arc seconds. So this depicts the fact that the simplified model achieves almost the same performance as the current model. And it's definitely something that we should consider for our future establishment of the pointing model. To conclude, I know I'm almost at the limit of time. So to conclude, this project enabled me as a student to acquire a solid understanding of telescope operations and pointing model mechanics. I had the opportunity to participate in an on-site data acquisition at La Silla. So that was during last technical mission in December 2024, where I gained a lot of hands-on experience, which benefited this project as well. I built and validated a custom pointing, Python-based pointing model that replicates C-point score logic. And this has been tested, validated, and is integrated into the telescope system. In terms of automation, we are more on a semi-automated approach. While it is true that the data acquisition, the offset extraction, the model fitting and results, this is something that can easily be automated. The validation and terms update remains something that requires like manual inspection. But in any case, all the tools are ready to be deployed. Additionally, this project led to the resolution of a persistent CORALIE pointing error by actually correcting that matrix that I presented in the methodology. But then in the new framework, we are going to be employing astrometric plate solving for CORALIE as well to avoid such errors related to so many transformations and so on. Something I didn't present here, but that I also did, was the analysis of all archival data for ECAM and CORALIE. So that was over 15 years of data for ECAM and around 6 years for CORALIE. And this enabled us to track the long-term pointing trends of the telescope. The results of this analysis have been fed into the new monitoring system, which would serve as a baseline for evaluating the performance of future pointing models. Additionally, something I didn't present here, I investigated the field rotation for ECAM, and this is something useful when we want to perform accurate photometric measurements using ECAM. Usually there is a residual field rotation, and I studied how we could mitigate to the highest degree this residual rotation. Also, I delivered a complete documentation on SharePoint on all the aspects related to the pointing model, so image orientation, conventions, and so on. And lastly, all the scripts used in this routine are available on the university's code repository. So just for future maybe maintenance, this might be useful. So overall, I can claim that my mission has been accomplished. So while some limitations, of course, were identified, the tools are ready to be deployed. They have been tested and they work. So this has definitely been very beneficial to the project. So I would like to end by actually thanking my supervisors for their valuable guidance, support, and feedback throughout the project. And also special thanks to the technical team, from which I learned a lot while at La Silla, but even afterwards, I got a lot of hands-on experience and knowledge from all the experiences, and this really benefited this work. So Now we can move to the questions. And sorry for being a bit long.
Did you, and I suppose that we start with you, François, and then Nicolas, and then
what were the scientific requirements for Euler, ECAM, ECAM, CORALIE, CALAO? What was the requirement in terms of accuracy?
I would say
What was the need, scientific need?
Yeah. So in terms of pointing accuracy, I would say we are on the standard. So typically we want to reduce the pointing error as much as possible. So I would say lower than like 5 arc seconds. Yeah.
So we have the same requirement for CORALIE and ECAM in terms of what will be the impact on the scientific performance for CORALIE and ECAM? CALAO, but I'm not sure that you...
No, I didn't. So for ECAM, as we saw, the impact of that pointing error is direct. Like we can clearly see that under long exposures, stars are going to be elongated, deformed, and this can affect the precision of our measurements. For example, I mentioned high precision photometry, so clearly this has an impact. Now for CORALIE, it's a spectrograph, but then we still want to be able to appropriately track, to point at the star and track it for the acquisition of the light. So an inappropriate pointing model, of course, will lead to wastage of time, maybe the algorithms to find which star, where it is in the field, and whereas if you have a good pointing model, it's almost there. So it's easy to identify by the algorithm to identify it and just place it in the middle of the fiber and begin the acquisition.
Like to add here that we didn't actually give scientific or technical requirements to Albert. We just said that we should look into that, and there is actually, because we were not satisfied with the, let's say, there were things we did not understand and which were not reproducible. So we didn't start from scientific requirements or technical requirements. So we didn't give them to you, just for information.
About the calibration state, so what are the lessons learned in terms of number of points? Is there some requirement, or let's say, in terms of calibration duration? How many hours do we want to recalibrate the pointing model? How long it takes? Is there a constraint on the number of pointing? How long it will take to do it?
And also, can you?
Yes, how many pointing? How many hours in a given technical night?
Okay, so for it, in order to establish a pointing model that's usable, here, for example, we have ECAM. Typically, 25 to 30 points are enough to have a good model. Here, for this pointing model, we used, I think it was 25 points. So, yeah, with 25 points, we are up. But if we want to have a really robust model, we might go to even 60 points. How long does it take to establish a model? So now, let's begin maybe with the time to acquire the data. So the exposures for ECAM, the standard exposures are 60 seconds. So with this, with 25 points, you have like 25 times 60. So maybe 1 hour, 30 minutes, so 2 hours, like, yeah, something like that. And then after we have that data, we need to process it. So we need to run the scripts, extract the offsets from this data, and feed the model. If all the tools are ready, that's something that can take not long. I would say maybe 30 minutes to 1 hour. I would say like 1 hour because then we still need to analyze the results. So overall, something like 3 hours with all the tools set. Yeah.
Yes. What about the ensemble in terms of if we identified some specific flexure of the telescope, need to do the re-equilibrate of the telescope? Did you see some hysteresis of the pointing direction? If you go towards east or west, you see a hysteresis error. I mean, from all your measurements, do we have a lesson learned from the telescope behavior, let's say?
Yeah. So actually, this I described it in the manuscript. I think that was in under the limits, the operational region of Euler, and using a data set where I went up to 20 degrees in elevation, I showed that the lower we get, the more nonlinear the behavior gets. So yeah, in order to have optimum performance, that study suggested that we can remain within like 30 to 83 degrees. That's really an optimum region. And of course, that's probably linked to the flexure, but maybe the atmospheric refraction, the fact that when we go towards lower elevations, we have that non-linearity and things get a bit, the pointing deviates a bit from the normal trend. I would suspect that it's linked essentially to the atmospheric refraction. Maybe the model, I don't know which model is used, I have not checked, but that's something definitely maybe to check. Maybe it's probably the atmospheric refraction model, but also could be due to the flexure. And for the symmetry, we can see it here. Just 1 second. Yeah. Okay, so this depicts the fact that these are the corrections that are applied by this model that models very well the pointing behavior of Euler. So, of course, it's not symmetric. We can notice that in some regions, for example, if you look at the left and the right, you notice that towards the right, you have higher corrections applied than in the left region. So, yeah, clearly there is some asymmetry.
Re-equilibrate the telescope or to do some intervention of the tube?
Can I just ask, what do you think could be the reason for this asymmetry?
Errors, of course. Now, it's true that if things were perfect, they would be perfectly also symmetrical. So if we take, for example, a look at this pointing term, this one here, so AN and AW. So actually what the model is a tilt of the azimuth axis, north, south, and east, west. So if that axis is maybe slightly tilted towards the left, it's clear that we are going to have such asymmetries, and probably that's what we can guess looking at this structure. So it's just, yeah, tilt of axis, I guess, that introduced these asymmetries.
So it's also about the image elongation.
About?
The image elongation.
Yeah.
Mm-hmm. So for me, it was not clear if there is also a component coming from the tracking error. Tracking or the telescope oscillation. How can you mitigate or discriminate between an error on pointing and the oscillation or error on tracking?
Like, how can we distinguish? You mean, I don't know if this
one. Are you sure that your image elongation is only pointing error?
Okay, so typically a pointing error would lead to tracking errors, because if we can't accurately point at the target, it's clear that under long exposures, it's a matter of fact, we are not going to adequately track, because tracking means we constantly adjust the axis to remain on the correct target. So if we have not in the first place, if you are not close to that target, it's clear that under long exposures we deviate. So I would say pointing errors will lead to tracking errors.
Due to field or rotation?
Due to the rotation of the Earth. Because ECAM, for example, has a D rotator. So field rotations are mitigated to like 0.02 degrees based on the studies I redid on this on the appendix. So due to the rotation of the Earth, mainly, I would say.
Can I refine your question? Because you were asking about oscillations, correct? So you didn't show, but in the manuscript you showed elongated images.
Yeah.
If I understand your question correctly, is how do you know that this elongation doesn't come from a fast oscillation, but from the pointing model?
Yeah, that's a good question.
You have a good answer in the manuscript.
It's true that the oscillations, I didn't evaluate it, but upon discussions with Bruno, I think he confirmed me that from a technical point of view, things were working fine. Like he told me the gearing errors, those kind of things were all functional. So reason I'm more on the side of pointing error.
Sorry to
yeah.
You mentioned you showed also the images after doing the pointing model.
Yeah.
Correct?
Yeah.
And how are they?
And
how are these images after correction of the pointing model?
Yeah, they are round. Yeah.
They are round. So why they are round?
Because you have a good pointing.
Exactly. So you corrected it. If it was oscillation, you would not have corrected.
Yeah. Indeed.
Sorry.
Yeah, exactly.
Like you, they are not there. Yeah, but they're much rounder.
Yes. You did not show, but on your report you have also monitoring of pointing error. Did you link some pointing deviation with specific event? I mean, here again about lesson learned, what is the impact of equipping the telescope, technical intervention, installation of CORALIE, etc., etc.
The pointing, that's what I mean. The impact of all that on the pointing. Yeah. So a very good question, actually. During last mission, typically we first do the necessary maintenance, so recording, maintenance, and everything. And lastly, we are going to align the mirrors because during recording, of course, we display several components. So we will align those components before we establish the pointing model. So the pointing model is really the last step of that chain, just to ensure that we don't move mirrors or components which would lead to errors. So it's the last step of the whole maintenance.
Previous events did not really identify the cause of these events. I mean, or maybe you know the information.
Yeah, I think it's extremely hard without the geolog.
Yeah.
Even in case where we were all looking for it.
And there were also sometimes bad, there were effects that we didn't understand in the pointing model. So we remember.
Yeah.
So that was like the way the motivation of his master's thesis.
Okay, that's all. Just wanted to add in your report also the people use Excel scale of ECAM, CORALIE, guiding camera, etc. is missing information. It's important to this information before.
Oh.
It does not appear anywhere.
Oh, yeah. Yeah. Probably I missed it in the document, but actually they're in the scripts, but they were supposed to be explicitly mentioned in the manuscript. Yeah, totally.
Nicolas?
One question about the legacy method for CORALIE. So today, are we able, because one of the points which was an issue in the past is that we were not able to restart from an existing model
and then do a pointing model with CORALIE, because then you have to correct the model that you have set instead of having 0 for all the parameters. So with the, if I understood correctly, it was in T-point, it was the T-point procedure was not able to do this with your new framework in the Python scripts. So are we able today to do a pointing model using an existing one which is not set to 0?
Yes, yes, and that's actually what we were doing in the legacy method. Yeah, so essentially, we take ECAM's model and we use it for CORALIE. As I said, just to ensure that, so just to ensure that our star is in the field of view, we measure the offset, we do all those computations, and in the end, just as you said, we draw the corrections of ECAM's model to go back to raw position. So yeah, we can work with an existing model. So it's like we implement the corrections at the start, and at the end, we withdraw those corrections in order to have the raw pointing behavior. But the main limitations of this method actually is that we are prone to a lot of errors. And as you can see here, this depicts these errors that span, I think, maybe for a year or more than a year, actually clearly illustrates the fact that we are vulnerable to, inappropriately calibrated transformations. So in the new, let's say, paradigm for CORALIE, we are just going to be using astrometry. That simplifies a lot the process, and yeah, we avoid so many transformations.
Yes, and linked to that, because the next question is how do we have to proceed for Calao typically, because the field is very small. Mm-hmm. So probably, do you think we can use the, I'm not sure we can use the...
Yeah, we can reset to 0 and use astrometry, that's what we mean.
Yeah, so for Calao it would be an issue, right?
Yeah, it's true. I wanted to work with Calao, but time didn't permit. The field of view is really small. So I think we may have to test, maybe do long exposures and see the maximum number of stars that we can get in the image. Typically, if we can get like 7 stars, astrometry would work. Now, I don't know if we can have this number of stars in Calao. Maybe, I don't know if tests have been done on that side. I cannot say with certainty because we haven't tried. But if that doesn't work, then you might have to use maybe CORALIE's model on Calao. And at the end, we draw the corrections. So, yeah.
So we are able then to take into account the already set pointing model.
Yeah, then we'll have to, but that's something that we really have to maybe check with Calao and see maybe what's the best method. I cannot say 100% with certainty.
And then I have questions on one of your slides. You compare the results between the RMS on ECAM, on CORALIE Legacy, and on the CORALIE new method. And you said that you had some better results with the CORALIE new method compared to that one. But if we look on ECAM versus CORALIE new method, which is exactly the same concept, but we see a big difference. How do you explain that we have better results on CORALIE astrometry compared to ECAM astrometry?
Very good question. So the difference stems from the pointing data. So with ECAM, you'd notice that here we had like 25 points. With CORALIE astrometry, we had fewer points. I think 21 points. So, and also the points, so for this method, you can see that the point, we don't have the perfect spiral, and the sampling near the zenith is not very good. So that will account for the fact that, for the difference already in the RMSs of the fits. So here it's low, but that low value might not appropriately capture the errors near the zenith. because the sampling here was not good. So actually, for ECAM, I would say it's probably better than even CORALIE astrometric method, taking into account the fact that the sampling is very good, low elevations, high altitudes, it's very good. And even though we are having 2.5 arc seconds, this might still do a better job compared to this where the sampling was not good and where we have low RMS. So that can account for that discrepancy.
So the data set was the same in CORALIE on the two right, correct?
This one and this one.
On the two CORALIE legacy and CORALIE astrometry.
No.
No, that's not the same data set.
No.
So it's more or less the same data set, or could your explanation also apply between the two CORALIE legacy and you said that there was a bigger data set on the left,
yeah,
and better sound.
Yeah.
Is this also true for CORALIE legacy?
So I would have to say that during the data acquisition for CORALIE, in principle, we use a spiral grid. So for ECAM, you clearly see that we have a very good spiral. For the two CORALIEs, not only was the sampling not, especially towards the zenith, not very good, but also the arms of the spiral were not like symmetrical. So they were a bit skewed. So I think maybe during the data acquisition, there was probably an issue with the script that we ran. But this has been corrected. So
so probably it's not a matter of the technique or the instrument, it's just a matter of the number of samples that we have. So.
Not only, because I did a test. So I did some tests and actually realized that when using this method, we get a slightly better accuracy than here, due to the fact that there are some transformations that we totally bypass. So fewer transformations, slightly better results, but it's more or less the same. Yeah, in terms of accuracy, if we use the same number of points, very good sampling would have more or less the same results.
There is one other parameter in addition to the RMS that shows that the astrometry method is better. Okay, because if you look at the errors on the fit, I mean, for example, the last parameter, basically the value, the sigma is much bigger in the legacy program. So it's less well defined. This is probably because there are less data.
There are less points, exactly.
Exactly. So despite the fact that you have more data points in the astrometry, you get a smaller RMS. Correct?
Yeah. 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 Exactly.
Another question, which is probably more an advice for us for the future. So if you had to define some parameters that normally shouldn't change the time, even if we change just the motor, or if we change the software, or we change something, there are some parameters that probably
should not change.
And for us, especially for me, it is important to understand in 3-4 years when we do something on the telescope, and we ask ourselves, is it correct that all the parameters have changed or not? So which one can we identify as being, let's say, almost constant, unless there is an earthquake or something that's completely changed?
Okay.
And in the complement of this, on which parameter we have to focus every month, and probably there is only a few which will change. We go new pointing model every 6 months.
Okay, so by referring to parameters, I'm not sure if you're referring to physical conditions, like atmosphere. I don't know. Are there physical conditions? So I'm not sure which exactly.
So you compute, you make a measurement, you put terms here, and are there some terms that should have some constant value that you can check in the past and instead
In the future. Yeah.
and are there others that less relevant?
Yeah, so that's a very good point. Actually, the geometric terms can be used as a reference, and they should more or less be the same with time. Because unless maybe we change, I don't know, or unless for some reason the geometry of the telescope is altered, these terms, AN, no more pointing. So AN, AW, IA, IE, CA, and possibly TF because the tube will not change. So yeah, these fixed terms can be used as a reference. And I think this is also something that guided us last mission. Because when we're establishing the new pointing model, for CORALIE, there were issues, and looking at the values, if they don't, if they're not more or less equivalent to what we did in previous years, then we understand that there is something going wrong. So yeah, the geometric terms can be used as references. If the telescope is not changed, then TF as well. Now, for the nonlinear terms, more or less, maybe unless, I don't know what can introduce nonlinear effects, but I would bet the geometric terms can be used as a reference.
It's not the case for CA.
Pardon?
It's not the case for CA.
For CA,
That is it.
so there are two different instruments. But if you take a look at the CA here and here, okay, if you do a comparison between these two, they are more or less equivalent. Maybe a sign, a minus sign.
I would correct you. So I think only A and NW are really stable. IA and IE, they are very dependent. Anything that we do with alignment is just the zero of the colors.
Okay.
And I think CA, TF, and all the reflection terms, they are also.
Yeah, you mean dependent on
the model that actually, you will find different solutions that give the same correction with a different tracing of the stars. So yeah, so I think actually practically A and AW are the only one that if they are not right, you know your correction model is.
I'm asking maybe I don't know what the purpose of your question was.
No, it was because when we changed all the motorization,
Yeah.
then we tried to redo, so we were at the beginning of all doing this.
Yeah.
But the pointing for me was something new. And at a certain one day you told me, okay, but not all the terms have changed because we only changed the motor. We didn't change the flexure or the flexure of the tube. We didn't change the configuration of the telescope. And I was interested by if we redo it in 5 years, for example, to avoid really asking ourselves this question.
But just for you, also for the context, we were trying to find the star, but we couldn't find the stars. So we should start from the pointing model. So it's the legacy approach. Yes, in an astrometry approach, you do not care. Sure. And you basically start from scratch, and that's the advantage. That's the main advantage. You do not care.
Yes.
Yeah. So even if you do, and you cannot determine individual parameters independently from the others. You have to. There is no use or need to assume that some parameters are more stable than others, because you anyway start from scratch.
Okay, but if for a reason or another you recompute a pointing model and you have one of the term which is supposed to be constant which completely change, then there is something probably that we don't understand.
As long as you get a good pointing model, you do not care.
I mean, if
maybe nursery or something like that.
Maybe probabilities that should hit something wrong.
Okay, good.
Now maybe it depends on.
Yes, but it was my conceptual answer. Sorry.
But yeah, I think, yeah, as Bruno said, if we display some components, maybe during maintenance, then it's possible that maybe the zero possible, like the offsets from the 0 point might change. So yeah, it's possible that AN and AW. I haven't looked at the previous model, so but I'll be tempted to believe that maybe AN and AW can change because it's a tilt of the azimuth axis. Okay, now maybe I don't have the engineering, yeah, maybe to exactly assess, so I would stick to maybe what Bruno said.
May I add a question here? So, you identify, because this is one that's just come up, you identified CA to be very different for the two instruments.
Mm-hmm.
Can you tell me why? Where does this difference come from? And to help you, you should just think out what is the main difference between the two instruments' optical axes.
So one of the instruments, so ECAM is on the Cassegrain focus, and the other one on the NASMIC. So light reflects from a mirror before reaching the instrument. I mean, from the tertiary mirror, so M3 before reaching before entering the instrument. So maybe this might explain that, but also I'm not totally sure, but the camera specifications are not the same. The guiding camera has a pixel scale that's different. But okay, maybe this might not have anything to do with the pointing. So yeah, maybe just the placement of the instruments, the telescope might explain this.
What is CA? What means CA?
So CA is the non-perpendicularity between the pointing axis, so the optical axis, and the elevation axis.
What's this tertiary mirror?
It deviates the light from, it changes the pointing axis. Yeah.
I think it comes in the front, so that's my opinion. But you gave the answer, okay? I said
yeah. The configuration.
mainly. All the rest is the same, the two configurations. Okay,
Okay, thank you.
So just one question. So apart that we did not have the software, why do you think we thought that the legacy of CORALIE was the only one we could use? Or let's say, was it obvious that the new version would work?
So your question is, was it obvious that astrometric platesolving worked for CORALIE than the Euler method? I don't know if I got it well.
So what is the difference between CORALIE and ECAM that made it not that clear that it would work to try to have enough star in the field?
Yeah, so essentially it's the field of view that raise, that doubt. Pardon? I didn't.
No, but maybe because I'm not sure about your question.
So if you make a very long exposure with CORALIE guiding camera, what happens?
It would be saturated.
Okay, so you want to know. So sorry, just to understand.
So you
What is the main difference when acquiring the pointing model or pointing data between the two? You have said there is the field of view, which is one of the difference.
Mm-hmm.
But there is another difference, and that's what you want to know. What is the other difference apart from the field of view?
There is a pixel scale that's also different. Yeah, but yeah, they're not the same.
The difference that impacts the number of stars that you see. Is it correct? No?
I think the problem is, think about making a very long exposure, 5 minutes with.
I think
with
the instrument would be saturated.
No. Imagine that the detector is capable to perform. That's another problem.
Probably linked to the specifications, to the technical specifications of the instrument, I guess. Yeah, I may have to think about it, but maybe I'm not seeing clearly what you mean.
I have to be sure. I don't know the true
So there's another rotator. Yeah.
Okay.
What did you say?
It's ECAM complex.
Yes, but then if you want to make a long exposure with CORALIE, then one of the limitations is field rotation. So that's why we didn't think to try. Even there, then it works. Perfect.
So, see, I didn't know the answer. Yeah, because if you make a long exposure to have enough stars, then you may have field rotation.
But field rotation is not an issue for astrometric plate solving. I think maybe the field rotation might just leave long trails in the image, making it difficult to.
I mean, astrometric software resists to a reasonable level of trace. So if you have a star that is elongated by 2 or 3, maybe it still works. And it's probably perfectly enough for a pointing model, especially for CORALIE, but in general, yeah.
So this means also that CORALIE pointing model, the astrometric pointing model, becomes less accurate when you go to higher elevation because of faster field rotation.
Yeah, that's also yeah. The rotation increases exactly, but then I would say I'm not totally convinced because upon analyzing many plate solved images for CORALIE, sometimes I saw field rotations of 90, maybe even more, and they solve correctly. So I don't know if this is really the main 90 degrees. So
you do a quarter of circle of the star and you still solve the.
Yeah.
The circles will.
It takes a walk.
Pardon? I mean,
so the trails were 90 degrees.
No, I mean, because when you analyze the output from astrometry.net,
never by 90 degrees.
Yeah, exactly.
Yeah, that's not the problem.
No, that's okay.
Because the astrometry can fit for it.
No, the rotation is not an issue per se. The issue is that you have a trail. So never had a 90 trail otherwise.
When you do a long exposure,
yeah,
because you do not field rotate the guiding camera, the images will be more and more elongated.
Totally. Yeah.
Yeah. And if they are too much elongated, the astrometry will not work.
Yeah, I totally agree.
But what you were describing was the image rotation.
Exactly.
Absolute number
which is not a problem.
The rotators north is rotating by a lot. And it depends where you point. But the question here was, if you stare here, you start at this position and then you will slowly drift. And that's.
Yeah, there'll be long. Yeah, totally.
But probably I will ask you to show me again the images just to, but I think it wouldn't work if the framework that big. And that's fine. I mean, even if you have, as I said, 2 or 3 times the width of the star and the trail.
So if I can identify patterns, I mean, if it succeeds to identify a pattern, then
it's fine. So that was.
Okay.
Okay. And if I may make a few stupid questions. Can you go to slide 12? old is this picture?
Ooh,
Just tell me things that you can tell, the facts.
I would say, so here we see that the telescope is still new, so I would say it's probably at the time that the telescope was, I don't know, I would say over 15 years.
Yeah, but there is one other element here that you can tell, which is important.
About the age, I mean, about
the age of the telescope. Or the time when this picture was taken. Not in absolute terms, in relative terms.
So I would say I can't see ECAM on that.
Okay, good. There wasn't too. I said that it was, sorry. Slide 7. I don't remember the question. There is an asymmetry between this left and the right part. You didn't describe it in the same way. Something is missing on the right part.
You mean for the equatorial mount?
Yes,
on my right.
Equatorial. Yeah. So I mean, equatorial mount and azimuth mount are not described in the same way what regards the transformation.
Yeah, so with the equatorial mount, so maybe if we come, so on these celestials,
don't go too far away. Stay on slide.
Okay.
Yeah. Don't think too much.
So for the transformations, the declination does not change for the declination coordinate.
So you're right. On the right side, you didn't transform the declination.
Yeah, totally.
It's true.
Yeah, it doesn't change, but I had to add that it stays.
It doesn't change if is it the same value? So you just keep the same. I mean, there you have right essential declination, which transforms in alt azimuth. Right essential declination is, these are parameters, celestial coordinates. Okay, and they transform to alt azimuth, which are what kind of coordinates? Do they belong to the star?
Can you rephrase your question? I'm not sure I got the last part of the question.
Yeah, so alt azimuth are coordinates of what? Of the star?
Yeah, so we transform, the coordinates, the right ascension declination into alt, so they're the coordinates of the star in the reference frame of
in the telescope system.
Yeah.
Okay. Alt azimuth are values of the telescope.
Yeah.
Okay, good. And over there, you have right ascension, which transforms to our angle of the telescope.
Yes.
Okay, what happens with the declination? It just stays the same, so you can take exactly the same value.
That's what I said earlier.
No, it's a question.
Okay.
Can you take exactly the same value because you didn't transform it?
So I would say maybe with my need to take into account the observer's local time. That's a good point. I didn't include it, and because in my mind I visualize that it stays the same because as the Earth rotates, we are actually moving away from that right ascension point, but vertically there's no motion, so I kind of assume that the declination would stay the same. But maybe it's not accurate.
If you have to set the telescope to a given declination, what do? What command will you give it to the telescope? Set position of the star, correct?
Yes.
And how do you, if you would do it by hand, what would you do on your MEAT telescope or celestron telescope you have at home?
How will I do it manually?
Yeah.
I would need a reference point. So the celestial equator, so that plane, I can measure the declination from.
How do you measure it?
No, using an instrument. So it's kind of an altitude from.
Okay, so there is maybe how to do it in practice on the telescope you have at home. You have a telescope at home?
Yeah, I have a small one that's out as in it.
Okay, it's not as okay, so it's all just practical. Okay, you have one of these celestron telescope with a horizontal mount. You set the polar axis and so on, and the hour angle, and now you have to point the star. What will you do?
Already, I would have so I would use these two axes, right ascension and declination. So I would have to point at the radial coordinates of that star, but then account for the time at which I'm observing that target. I'm not sure this answers your question about the declination.
For the declination, yeah. Sure. This does depend on the time. Well, okay, on your instrument, normally, probably you have operated such a telescope, but you would turn the hour angle and the declination of the star, since you know that it's parallel to the equator. You can just go on there is a scale, and you can set the
like a compass,
declination on the scale. Okay, if it's at 67 north, you can go on this scale, there is 0 and 90, and you can set it 67 scale, 67 degrees. It's as easy as that.
It's difficult to believe because I don't have equatorial, I have this one.
The question. Are you sure that your star will be in the center of the field when you set it manually?
If we don't take into account those corrections, no. I mean, these corrections.
Yeah, but there you didn't put any correction for the declination. So my question was this: you assumed that if you give the command, go to this value of declination on the telescope mechanical axis, you will be perfectly on the star in declination. This is not the truth, but that's what you wrote here. There is no transformation from the declination, the celestial coordinate, to the telescope declination. So you should add this. Okay, on the left side, you have the rate ascension and declination of the coordinates of the target. And on the right side, you have the coordinates of the telescope. Now, for an azimuth mount, this is add as. And for an equatorial mount, this is hour angle and declination of the telescope.
I missed the declination. Actually, I thought, maybe it's naive, I thought the declination would stay the same for some reason.
It stays, but there is a transformation between the theoretical value and the applied value.
Declination of the star, declination of the telescope.
Yeah, the declination of the telescope must be the same as the declination of the star. But since you cannot guarantee it, you need a pointing model at the end that relies the two. So there is a transformation between. Okay, good. This was even the more sort question. But since you described it, I think it's important also to understand what you are describing. And And the description here of the equatorial aspect was incomplete, in my opinion. Maybe a more a last question, more practical.
Mhm.
You said that everything is in place. The only thing that is a little bit manual is the validation in the pipeline. Why? Or what makes the manual validation manual?
That does require.
From an expert.
No, you can do it manually.
That's not.
But what makes it? Can you automate it? Can you make it automatic? Or is there a need that you encountered? Basically, when you fit and you do optical manual validation, have you encountered situations that in 50% of the cases where you have to reject the model? Or could you imagine that it is so reliable that you can make it automatic?
I'm not certain. Indeed, we can make it automatic if we define some rigorous criteria. For example, the RMS, but the RMS alone is not enough, but that's a starting point. Now the analysis, I didn't show the image here, but in the report it's there, the elongations of those stars. So after analyzing the morphology of the star, we can maybe say, okay, if the value is lower than 0.1, then that's also indicative of a good model. As regards to the other criteria, just 1 second. Validation.
Oh man. No. Okay, I stop here. Okay, we eliminated all the grand public, that's fine. Thank you very much. So we stop here, and there were a lot of questions already. So thank you very much, and we deliberate very quickly. Ok?
Yeah.
Je dois t'amener en voiture.
Sorry.
No, it was my fault. Okay, good. Thank you very much. And so we deliberate, and then how does it? Then we communicate the grade after immediately afterward.
Yes.
Yeah. Okay, so we get the answer after the deliberation.
Okay.
There are 2 grades, for the manuscript and for the presentation.
Okay.
Correct?
Yeah.
Yeah, for the work and for the presentation. Okay, thank you very much.
Thank you. Let me stop this.